Now, shall we look up, please? So from page 79, Shiraz, where were you for ICT earlier today? Again, missing classes for me. Okay, and where's MB gone? No. Yes, it's still page 81. I haven't changed my mind. So, from 79, what's wrong? Page 79, I don't feel like there should be any questions on it, because it's just a matter of using the table. So I'm not going to look at anything from 79. I'm just going to go straight into 81. So, if you think back to some vocabulary here, turning points. We did turning points actually when we did quadratics. The turning point was the minimum or the maximum point on the graph. But what's nice about derivatives, it lets you find the turning point for any graph. And how does it do that? Well, what you notice is when you look at a graph like a cubic, the slope of the tangent, so Mohammed, what is the noun that means slope of tangent? No, you're way off. Somebody give me the noun that means slope of tangent. No. No. Derivative, guys. Yeah. You're too far away. And then what is the verb? Differentiation. Great. So anyways, the derivative here will be 0 because it's a horizontal line, and the derivative here will also be 0. So if you would like, no, come, just about, come on, why are you late? I'm sorry, this is not a reason for being late for maths class.
It just finished. Yeah.
No, hang on, dude, again, this isn't a reason for being late for maths class.
Okay.
Yes. I am sorry to tell you this, but this isn't a good reason for me for being late. Yes, so you know in future, make up a reason, don't give me this, okay? Right, here, slope of tangent is 0 at the top, and slope of tangent will be 0 at the bottom here. And anyways, if you were late because you were praying, I want to see you burst through that door like you're worried that you're going to be late for maths class. You know, you came in too casually like, yeah, time for maths. You know what I'm saying? I want you to at least look worried as well. Okay, so let's go with an easy one first. Let's go with a quadratic. Yes? Sorry, you're the only one looking around here. It's like, anybody go back? No? Sorry. Right, so let's look at a quadratic for an example. Y equals x squared plus 2x plus 10. So we know the shape here. It'll be like this. So if I want to find the turning point, which is down below here, what I do is I calculate the derivative. The derivative is 2x plus 2. And I make it equal to 0. Therefore, x equals minus 1. How could I find the y? substitute it in here. Yep. So y equals 1 minus 2, which is minus 1, so y is 9. So the point down below here is minus 1, 9. You better start writing. If you know what's good for you, you better start writing. You better be fast. Yeah, no, come on, faster, come on. Yeah, there we go. All right, now, to the side for the moment, I'll go back to this, don't worry. Let's use the technique we learned in earlier in the semester. So we have y equals x squared plus 2x plus 10, and then we complete the square, so what do we get here? X plus 1 squared plus 9. So what would be the turning point here? Well, look at that. So it's the same. But what's great about using this technique is that it'll work not just for quadratic, but for any type of graph. So we'll look at a cubic now in a moment. So write this example down.
I think you said that I didn't hear.
Say what?
No, why the graph is like that? Because
Oh, I definitely said this before. Definitely. And the reason is because it's positive x squared. It's an x squared, not a minus x squared.
X squared alone without quadratic.
No, in fact, x squared alone or not is unimportant. The only thing that is important is what's in front of the x squared, and that controls everything. So yeah, no, I get what you're saying. It doesn't actually matter if there's extra pieces or not. Did you write this down? Did you really?
Yeah.
Show me. Next time you lie to me, you'll regret it. Now write all of this down. Okay, let's have a look now at a cubic as an example next. So example, y equals 2x cubed minus 18x squared plus 54x plus 20. So what I'll do, it'll be handy to have the program open for the graphs. Okay, so we know the shape of cubics because we've drawn them before. They go down and then up, back down and back up. Well, certainly in this case because it's 2x cubed, it's a positive x cubed. So when we picture this one here, actually let me draw it, that'd be handy. So can you just read the cubic back to me? What was it? Y equals, oh actually no, 2x cubed, yeah.
18x squared
Plus 54.
54x
There we go.
is 20.
Oh, I must have miswrote it. That should be 30 here, okay. Alright, let's draw this. Zoom out. What the heck? I must have typed something wrong in here. 2x cubed, yeah.
Minus 18.
Minus 18 here, please.
Plus 54.
Alright, let's try this again. It's awesome. Is that, yeah, that's how the sentence is going to finish, isn't it? Okay, zoom out. Oh, it's weird. Alright. Zoom in. Oops, too far. There we go. Yeah, so it's a bit hard to see here. If I was looking at this graph, where would you say, just look at the x-axis, the numbers, where would you say where the turning point is? And what I mean by turning point is where the derivative is 0.
Roughly around 2.
Maybe 4, maybe 2. If you look, this is where it kind of levels off as flat. So we are expecting an answer between 2 and 4. So let's see what we get. So, like normal, we differentiate. So the derivative will be 6x squared minus 36x plus 54 equals 0. I can divide everything by 6. X squared minus 6x plus 9 equals 0. And solving this, actually I think I just get x minus 3 and x minus 3. So, no surprise, x equals 3. And to find the y, I substitute it back into the original. So somebody please put 3 into that and give me the result. I think it'll be quite large, because if I look back at my graph, it should be around about 100 maybe. The first step? You mean from here to here?
Yeah.
For real?
Yeah.
I differentiated and found the derivative. So you can double check, but I think it's 84. What?
7.
No, you're going to make me come down and I'm going to look at your calculator and you're going to have something typed in wrong. Give me. Back. What's at the back of his calculator? Yes? Right, okay. No, I'm not getting off my seat again. You typed it in totally wrong if you got more than 100. Did you put x equals 3? And did you put it into the original? That's this one here. And did you properly use your brackets? So if I go down, are you good?
I don't know what this is.
Gone off the screen. No, I can't. No. You should, if you do this, you should always type it in one go, in once, not bit by bit, because that way you make a mistake. It's easier to go back and change it. Okay.
So we should put brackets between every calculation.
No, it's not. No, it's not necessary because the x here is positive. If you like, when it's negative, you can use brackets to be safer. In the case of when x is positive, it's okay. You shouldn't need brackets, you know. Okay. Now I'd want to look at a cubic now, but a cubic that has more than one answer. Okay, so like before, Mohammed, we will differentiate, and then what do we find when we differentiate? The derivative, yes. Yeah. I get worried sometimes. I worry, you know. The vocabulary, I know. Yeah, I know. Yes, yeah. So, differentiating, I now will have the derivative. (6x squared plus 42x plus 72 equals 0). Yeah, that looks right. I think 6 goes into all of these. Maybe 6 go into all of them.
Yeah, we go.
That's x squared plus 7x plus 12. It's 12, yeah.
What if I didn't divide? Just I leave it in.
Yep, again, I'm doing this without a calculator, so I'm simplifying it first before I solve it. Yes? Because remember,
Too much calculator.
yeah, and?
And then
That's right, yes. Right, okay, so here we got 4 and 3. Minus 3 and then minus 4 will be the two answers. So I'd like you please carefully to tell me what the y is for both of these. So what did you get for the y?
Minus 69.
Good job, Amjad. And then the next one? Good. So I'd like to draw the graph, so let's have a look at the graph. I'll go back to this, don't worry. So typing it in, it's y equals 2x cubed plus 21x squared plus 54x, no, plus 72x plus 12. Let me try and exaggerate this a bit. Yeah, let me do center here. Yeah, so if I was to look here, I'm trying to. Yeah, my axis has disappeared from the top of the screen, but you can see here it's flat, then it dips down, and then it becomes flat again. So if I just get my axis back, so you can see the first one looks like it's at around about minus 4, and then the second time is at around about minus 3. It's difficult to see. If I draw it like this, it's clear to see, but the problem is my axis has moved off the screen now. Okay, but you can see when you do the right scale here, you can clearly see the up and the down. So you get two locations when the derivative is 0. I'll go back to that there. Maybe if I, no, yeah, that's a bit better, I guess.
then you go from up to down in the point of 72. Right?
Yeah, it looks like it's about minus 60 something on the graph, you can see. But let me try and fix it up a bit. Don't confuse me, Andy. Close enough. So you can see there you've got your two little turning points. Anyways, what were they? So you can see they're both negative numbers. So the first one was minus 3 and minus 69, and then the second one is minus 4 and minus 68. Not for today, but I mean it could happen in the exam. But in the exam, it's more normal that they ask you to draw cubics in the algebra question. And it's more normal that they give you the graph in the calculus question. Yes? Okay. Now, A little bit of vocabulary here. On your workbook, I use many different words, but they all mean the same thing. Example: extreme points, turning points, critical point, stationary point, maximum minimum point. But they all, vertex, they all mean the same thing, okay? The most common term to use in the exam is turning point, stationary point, and vertex. Well, or even as well. Well, I mean, they could also say max min, but you all know what the words maximum and minimum mean.
Yeah.
So the new words for today would be turning point, which I've been using already, and then stationary point, and vertex, but we have that already from the algebra chapter, so it's really just stationary point and turning point. Okay? Right, now look, I want to show you there's a couple of different stationary points, okay? So this here is a turning point, for sure. It's where if you imagine the tangent here be flat. And then this one here as well. It's flat. Okay? But in fact there's also other types, like this. Here is also a turning point, a stationary point, because the tangent is flat. But there's a big difference between that one and the other two. And what is that difference?
Plus is 0.
Yeah, well that is true, yeah, but something else I'm looking for too. Yeah, if you look here, it decreases, increases. Here, increases, decreases. Whereas here, just increases. But what I'm thinking about here is that this turning point is actually a minimum. This turning point is a maximum. Whereas this turning point isn't necessarily, well, it's not a minimum or a maximum. But it's still a turning point. Yeah, now that will be different things, and that gets more complicated, which will be the next lesson. But then we have inflection points. But in fact, that might not even be an inflection point as well. It gets more complicated. But anyways, there's this one, and of course there's this one. So these are all examples of turning points. The key thing is that the derivative is 0 at these places. In other words, that the graph temporarily levels off. But these ones are nice ones because often it is the case that we want to find the minimum or the maximum.
But they're always touching one point.
Yes?
In the both down pages, they only touch one point.
Yes. No, not unless. Oh no, wait, hang on. You'll have to wait a few seconds. Yes, it only touches at one point, but in the bottom two cases, the one point it touches at, it passes through. So it does touch it once, but it runs through it. So it would look, if you look really closely at it, this point here, it might look like that it's passing through many, many, many points, but if you actually zoom in and look at it really closely, the more you zoom in, it'll maybe look a bit clearer to you that it's only passing through one point. But of course then if you start to zoom out, it will look like it's running through the graph. So no, it's still only touching once.
How do we know it in the exam? Just have to zoom in.
Yeah. You go. Like this. Your paper can't do this? Oh, I didn't know this. No. Yeah. There's a new paper app. Didn't know this. No, in the exam, what's more important for graphing in the exam is showing the key points rather than the accuracy, you know. Like for the exam, they really would give you the marks for the general shape and key points on the graph instead of how beautifully you draw it. It's not biology. It doesn't need to be beautiful graph, okay? Now, do one more of these, but a more difficult one. So, next now. Yep.
How can I discover from the question that there are points me to draw that shape or the option?
That is the next lesson. So, the next lesson gives us a way to decide what shape it is from these. Yeah, that's a good point. What we'll do in the next lesson is something called the second derivative. And the second derivative helps us to decide which of the four situations we are in. Okay. What's wrong? Ask. Next time. Right. Y equals log x to the power of 18 minus x squared minus 16x minus 2. I will use all that screen. Now, before I differentiate, what should I do? I should simplify my log. So what can I do with that 18 up the top? I can put it in the front. Now, I shall differentiate. So 18 log x becomes 18 over x minus 2x minus 16 equal 0. This looks somewhat familiar to what you did in limits. What's wrong? No, you know what to do next?
The changing of the x becomes 2x.
Yep.
And then 16x becomes the x.
Derivative of 16x is 16. It was one of the rules I gave you.
Multiply both sides by x.
Yep, we multiply everything by x to simplify this. So we'd get 18 minus 2x squared minus 16 equals 0. Simplifying, we get 9 minus x squared minus... Oh wait, hang on, I lost an x here. There's an x at the end here. Let me just fix it. 16x equals 0. So x squared minus 8x equals 0. Then we take everything to the right. X squared plus 8x minus 9 equals 0. So if I look at this, x minus 1, x minus 8. So we get x is 1, comma, then we have the y, and then we have x is 8, comma, and then we have the y. So if I put in 1, I get log 1, which is 0, minus 1 squared, minus 16 minus 3, so that's minus 19 here. And then can somebody put in the 8, please? Yeah?
For the factorization that you did, I think something is off.
Maybe. Oh, it is. It's totally off. You're right. Rewind. What are the factors here? X minus
1 and x
plus 9. Thank you. So it should have been 1 and minus 9. Okay. Right. So 1 is still minus 19. Okay, please put in minus 9. Now, warning time. The original, was the 18 in the power or down in the front? Was in the power. That is extremely important because if you bring the 18 down, you can no longer put the minus 9 inside it. Why not? Yeah? Log cannot be calculated for a negative number. However, if you leave the 18 in the power, what happens when you put the minus 9 in? It'll be positive because of the power 18. So it might not seem important, but it is very important that when you substitute something in, it must be the original with no changes whatsoever. So put the minus 9 power 18, and you should put brackets around the minus 9 then. And tell me what you get. Calculate that one, please. Get calculating?
I think it's 39.5.
Yeah, I'll have to double check that one. No. And the rest of the equation too, please. Got the calculator? Yeah, what are you calculating? Looks good, yeah, that's right. Okay, so what was it, Andy? 100.55 or something? What is it?
100.55.
Okay. Don't care. Right, let's draw this graph and see what we get. I'll go back to this, don't worry. So, y equals log x power 18 minus x squared minus 16x minus 2. So before I draw it, where did we think the turning points were? What x values? 1 and minus 9?
Yeah.
Yep, so let's see. So I'll zoom out a bit straight away. So we think there should be one about around here, and there should be one around about here. Now you see, isn't that a weird shape? But if you look here, minus 9, that's clearly a turning point, and what way would you describe it? Well, as a maximum. And clearly here, this is a turning point, and how would you describe it? No, look at it. You see, it's a bit strange. Andy, had a very stressful day. I really would love to punch someone in the face. You don't let me do. The one at the minus 9 is a maximum because it's like a hill, levels off. But interestingly, the one at 1, see where my cursor is, that's also like a little hill. You see here?
Yes.
So that's a maximum also. So what's interesting here is this graph has 2 maximums, which might sound strange because you think one should be a maximum and then the other should be a minimum.
Yes.
But here they're both maximums. Now, this is where I'll give you a little extra vocabulary, okay? Both of them would be called a local maximum. Look up, Fatima. Both of them would be called a local maximum. You know the meaning of the word local, like your neighborhood. So if you just look near the top of the hill, you would think you're at the top of the hill. And if you look near the top of the other hill, you would also think you're at the top of the hill. So they're both called local. However, only one of the 2 is truly the maximum for the whole graph. Which one is that? The minus 9 one. So then that one is called a global maximum. So just like in normal use of English, you have a local, which is like the neighborhood, and global, which is the whole picture. Please make note of those 2 words because they are important for this chapter. Local and global. Local, yeah, local, you literally just, almost like a magnifying glass, just look at a particular region.
Yeah, but you call it each graph, there must be local, right?
Yeah. For each graph there must be usually locals, and then sometimes it has a global, sometimes not. Like for example, in this graph here, would this graph have a minimum? You see, it doesn't really look like it does because you've got to remember, when this graph continues on, this is just going to continue going down the screen. So it goes down to minus infinity. It's not like it will go down and hit a bottom and then come back up. Because if it did, then I could call that one a minimum. Now you might be thinking, it looks like there's a local minimum in the center there, doesn't it? So let's zoom in and see what happens. So where would you say the minimum is? Looks like minus 70. Okay. So let's zoom in there. Alright, where do you think it is now? Minus 85. Alright, let's zoom in on that. So alright, where's it now? Minus 95. So can anybody see what's happening here? No, not black magic. What's happening here? Well, what's happening is on the original graph, go back. On the original graph, you can't actually see it. But what's happening here is this actually is shooting down to infinity. So although it looks like it's coming together, it's not. It's shooting down. So there is no local minimum at the center. But anyways, look at the original function. Look at the original function. Look at it. What values of x can I not use?
Negative 2.
Yeah, but negative is fine because it has a power 18. So it'll become fine. Yeah, the only value of x I can't use is 0. And what happens to my graph at 0? It goes to infinity, doesn't it? But that's not going to happen because we're not allowed to use 0 anyways. Okay? Yes?
So why is the bigger graph the global flexibility?
Right, let me put it to you like this. Can you show me a point on this graph that is higher than here? So that's called the global maximum.
Does it have minimum? Yeah.
No minimum because it shoots down to minus infinity.
No, because I saw both of them are going down from 15.
Yeah, they're going down. So hang on, let me show you. If I zoom out. See, if you zoom out enough, it kind of looks like from a distance what shape? Just like the quadratic, doesn't it? So quadratic, this one here has a maximum, but it has no minimum because it's just going down to infinity. Now, hang on. For those people who are interested in why does this look like a quadratic if I zoom out enough? Because if you look here, this scale now is in the thousands. Yeah. If you look at your function, you see it has a log x 18 and x squared is 16x and 7. As the x gets bigger, which of those terms do you think will contribute the most to the total of y? So I'll give you a simpler example, okay? If I said x squared plus 1 and x is really big, which of the two, x squared or 1, would contribute more to the total? X squared. So if x is 100, you would have 100 squared plus 1. So clearly the 1 is not important, the 100 squared is. Likewise, your x squared will be bigger than, what's beside the x squared? Is 16x, which will be bigger than 7. And in fact, log x, do you remember the graph of log x? What shape is it? It goes quite flat, it slowly rises. So in other words, if you zoom out enough and make the x big enough, it will be the dominant term, meaning that the graph will behave like a quadratic if you zoom out enough. This level of detail is not on the exam, but it is interesting for people who want to know why does this look so quadratic if I zoom out. Right. Yes. Now, which one's to try? So, can you circle these, please? Hang on. Don't please. Leave me alone. Write these numbers down. I'd like you to do H1. 15. Yeah, 50. Do question 50, please. 15. 17. 13. 26, 7, and 8. No.
26 and 7.
Oh yeah, sorry.
15.
Let me just stop the recording.